My name is Hans-Peter Hart. I'm working as product manager for Basic Color, and our company cares about color management. So from the start of creating an ICC profile for digital cameras, scanners, monitor, and output also. And in this special session today, I would like to give you a brief overview about the DeviceLink technology. What are the advantages, disadvantages also, and what is a DeviceLink profile? So before I would like to start, I would like to know a little bit more about you. How about your knowledge is about DeviceLink technology, so that I can also speak a little bit or get a little bit in more detail what's, for example, a rendering intent, special rendering intents. So my question to you is, if you could raise the hand, who is working already with DeviceLink profiles? Okay. Yeah, so it's half-half. Okay, so I have to make a little kind of mix, go a little bit deeper in detail, but also I'm trying to explain very easy what the DeviceLink profiles are. So first, I have to explain a little bit what is an ICC profile. An ICC profile is nothing else than a description of a device within my workflow, a color description. And as you can see here, I have profiles. So there's always, that's very important to understand, 2 ICC profiles are needed to make a color conversion. Because often customers say, okay, I've created a perfect profile, but it doesn't work. The result is not good. So probably the input profile was wrong assigned. And so, of course, my perfect best output profile I've ever created doesn't work because the input profile is not correct. So the ICC profile technology always means I have to take 2. So my source profile and my destination profile. And as you see, I have here 2 CMYK profiles. On the left side is the input profile with the device data, it's CMYK. And then the LRB is my so-called profile connection space, PCS, it's the profile connection space, which combines both ICC profiles. And during color conversion, it's very important. It's not technically correct, but if I'm doing an ICC color conversion, the CMYK value from my input data will convert it to LAB, and so every information is lost about the CMYK combination. So for example, if I have 50% black, I'm doing an ICC color conversion, then the 50% black goes to LAB, and my color value, the gray, doesn't have any knowledge about the CMYK combination. And then from this color gray, the LAB converts to CMYK. And then you will have a CMYK value of 4 color values. So, and that's one disadvantage of ICC profile color conversion. Here I have, for example, 2 color gamuts. The bigger the wireframe is my ISO-coated, and the smaller solid color gamut is my ISO newspaper color space. So that's also, everyone knows. If I print something on offset press, on coated paper, I have a huge color gamut. On the other side, if I print something on a newspaper printing machine, I have a smaller restricted color gamut. Here, I hope you can see it also here in the beamer. I made a ICC profile conversion from ISO-coated perceptual. That's now very important to understand because the four rendering intents in ICC technology are perceptual, colorimetric, relative absolute, and saturation. The saturation rendering intent, it's not, we can forget at least. The most important are perceptual, relative, and absolute colorimetric. So if I go from iso-coated, a huge color gamut, to newspaper, of course I have to decide which rendering intent should I choose right now. Of course, if I choose colorimetric relative, every color which is out of the gamut of ISO newspaper will be cut. So I have a flat, I have a really bad conversion. So the other solution is to select the perceptual rendering intent. And now that's very important to understand. The perceptual rendering intent is a table. It's a static, fixed table, which says every color will be compressed. So it's a compression table. And during ICC profile creation, all color vendors of color management software, it can be X-Rite, Basic Color, ColorLogic, who else? Yeah, some other vendors also. Everyone has his secret sauce about how this compression table will be calculated. So that means if you're doing a ICC profile conversion with, for example, the ISO-coated version 2 profile, ECI, it's created with Heidelberg, the software, and we have on our website also the ISO-coated version 2 basic color profile. So if you're going to convert with both profiles, an RGB image, for example, and the perceptual table, you will have two different results because Heidelberg has a different color compression algorithm than we have.
But if I would take the Heidelberg profile using your color conversion engine, I would get the same result?
No.
No?
No, not with the ICC profile, because the perceptual table is stored, let's say, within the ICC profile. Yeah. There are two things. There's the ICC profile and the CMM, that's the color engine, who will make the transformation. But how the colors are compressed, it's defined within the perceptual rendering intent.
Of the profile?
Of the ICC profile.
So the profile has more influence than the CMM?
Yes.
That's what I wanted to say.
Yes, much more. The ICC profile has the most influence than a CMM. In early days, let's say 10, 15 years ago, the CMM had an influence. If I took the Agfa CMM or the Heidelberg CMM or the Adobe CMM, I got during conversion 1, 2, 3% percentage color differences. But today, that's not any point anymore. Okay, so let's go back to have a look what happens if I'm doing a transformation from ISO-coated to newspaper. So ISO-coated big, newspaper small. So I have to say perceptual. And now you have to understand that this compression table is calculated during profile creation. And that is important to understand that the perceptual table must also work with an RGB image. So the compression is quite huge because the table compresses also colors which are in RGB. So that means if I'm doing right now a transformation from ISO-coated to newspaper, the compression is a little bit too strong because the compression must also care about RGB images. So it compresses too much. And
so the compression table is in the destination profile?
Yes, right.
It's not influenced by the source profile? Even if there is also a compression table?
It can be the so-called, some developers, so vendors making the so-called reverse gamut mapping. Okay. So if you're selecting, for example, in Adobe Photoshop, the perceptual rendering intent, what will be what happens? Photoshop takes the ICC profile of ISO coded, ISO newspaper, and the perceptual table, which is the B to A0 table of the destination profile, the A to B0 table of the source profile, and it depends of the vendors what they're writing within that table. It can be a link to the colorimetric table, but it can be also a reverse gamut mapping. Why they are doing that? So if you're making a compression, of course, colors will be lost. So if I'm going to another color gamut, they do it reverse somehow. So a little bit of, not extrapolation, but reverting the compression. So if we have a look now here, you will see every color will be changed because I'm compressing all the colors. I'm compressing the highly saturated colors, but also the flash tones will be compressed. It's like compressing all the colors in a smaller gamut. And now we have the perfect, cool DeviceLink technology. Why it's so cool? It's one disadvantage is, or I have to say one advantage of ICC profiles is that I have an ICC profile format: scanner, digital camera, newspaper, offset print, digital print, and so on. And I can mix everything together on the fly. A DeviceLink profile has very big advantages, but the disadvantage is not so flexible. A DeviceLink profile is a fixed connection of two color gamuts. So that's the disadvantage, but the big advantage is that you can make certain definitions, definitions of certain things I would like to show you now. Now, if I'm doing a DeviceLink conversion, I don't know, you have seen it. If I go back, my flash tones are not changed. They are not compressed because when I created the DeviceLink profile, I said the compression must be just a little bit. The compression must be so strong that I do not get any clipping, but it's not so huge, the compression, like in the perceptual table. So that means a DeviceLink profile cares about the source color gamut and compresses just a little bit so that I don't get any clipping. That's one advantage of ICC DeviceLink technology. And that's the way a DeviceLink looks like. The PCS, the so-called profile connection space, is cut out, and the two tables are connected. CMYK, CMYK, or RGB, CMYK, or RGB multicolor, or CMYK multicolor. So you can combine every ICC profile to a DeviceLink. And then, of course, the next step is that also this DeviceLink must be used somewhere. For example, Adobe Photoshop can use it, but it has a big lag, because if you're doing a DeviceLink profile conversion in Photoshop, the big mistake Adobe does, you have an ISO coded to newspaper with a DeviceLink, it works. But now it's the mistake that the image still has assigned ISO coded. And then the source profile, because Adobe is not able to assign the destination profile, which is defined in the PSID tag of a DeviceLink profile. So that's many years ago. This tag was defined officially in the ICC, but still today, Photoshop does not assign the destination profile of a DeviceLink.
That's same for Toolbox. You have to add it in the second step.
The output.
Yeah.
The output profile.
The output intent profile, yes, but that is also technically It's a different piece of software. There you have the single profile and the DeviceLink profile, as Hans-Peter just explained, is two profiles. So it's a source and a destination, the same ICC profile. So you would need to have for the output intent, you can't use a DeviceLink profile in the output intent of a PDF file. You would need to use a single source or destination profile.
Yeah. Same case for Photoshop.
Yeah, it's the output.
If you have your private ICC destination profile, which Photoshop has not, it cannot be extracted from the DeviceLink profile, the original ICC profile.
Well, there's in the DeviceLink profile, that's the PSID tag. That's just the name. So if it would work correctly on the system, the ICC profile physically must be within the color folder. Then the application, Photoshop, must read out the PSID tag, see, it's ISO newspaper, I assign it to my image. That's one possibility. The second is, there are two, I don't know if it's already official in the ICC or not, I don't know yet, or I don't know it for the moment, I have to check it, but there's also the possibility to embed the ICC profiles, source and destination, within the DeviceLink profile. So it can be extracted and assigned. And that's the P sequence, or I don't know, but I have to check it. But that's also possible. So this is a DeviceLink profile. So the advantage of a DeviceLink profile is the optimal transformation from print standard, from one print standard to another. It can be from offset to newspaper, from offset to gravure, from offset to digital printing. It doesn't have any limits. And the two big advantages, one we have seen already, is the gamut compression, the gamut mapping. And we are able to keep separations. So that's a big advantage. For example, if you have a customer with a certain logo, which must have, I would like to tell you now because it comes in my slides in a few seconds. Okay. One thing is processing of legacy data. As you probably know or probably have heard, we have a new standard for offset printing. For a few years, it's the PSO coded version 3, which is based on the FOGRA 51 characterization data, and the older standard is FOGRA 39, which is ISO coded version 2. I made a comparison of the two ICC profiles, and as you will see, okay, the primaries are a little bit moved. Here, for example, the cyan is a little bit different, the green then, and the magenta. And just two words about what's the difference, old standard, new standard, why this happened a few years ago. One thing is that FOGRA 39 is based on the M0 measurement data. Why that? I think it takes me too long if I explain this one. You just have to know, okay, the old standard is doesn't care about optical brightness in paper. The new standard cares about optical brightness in paper. And another difference is also the TVI. The old profile says 13% in midtone for CNY, 16% in black. The new standard says no, 60% for all 4 colors. These are the main difference of the two profiles. The paper white, based on the measurement condition, and the TVI. If we have a look here also, one difference is also then in the dark tones, the maximum black is different. The wireframe is my ISO coded version 2. So the wireframe, it's the old standard, defines a more darker color gamut for offset printing. The new standard not. So if you're thinking, if I'm doing a relative colorimetric transformation, I will have some clipping in the shadows, which is not good. Of course, now you could say, oh, I have the black white compensation. Yeah, that's true. That works fine for this compression in the shadows.
So that means that the new standard has a smaller gamut than...
Here in the darks, yes.
But same price.
Another new standard expanded.
Yeah, that's FOGRA 53 as connection color gamut, which is proposed by FOGRA and which is discussed actually vice versa. So, me personally, so my personal opinion, I don't know if that color standard or color space gamut in CMYK is needed, but that's just my personal opinion. Yeah. Then you will see here it's the PSO code, the new standard, an L of 12, and here the old of an L of 9. And the most known difference is here -6 in B. That means very bluish paper because of the optical brightness. So one of the big disadvantage of the old standard was that today no production paper with an LAB of 95, 0 -2 does exist in the market. All the paper manufacturers produce paper with optical brightness to get a very nice, bright, white paper. And so that was one reason why the new standard was defined many years ago. 2015, the profile was then created, and by the ECI also made available for download so that every customer can use it and can make the color conversion. So here I've got one of the images of Roman 16. And as you can see, it's in ISO code, it's old standard. If I'm doing right now color transformation with an ICC profile, what happens? 60% cyan, 100% magenta. Turns out that I have 58% cyan, 98% magenta, 1% yellow, and 2% black. So I have all 4 plates with a definition. If I go back, you will also notice the same what we have seen before. That also, again, the flash tones are changed a little bit. A little bit brighter, it's desaturated. Now again the same thing with DeviceLink technology. I think you will see it. Or you don't see that much because the color transformation is best fit to my source profile, and so not that much has been changed. And here with the DeviceLink, I had the possibility to say, okay, keep secondaries, so that my secondary color won't be infected with yellow and black. Of course, now if I'm calculating delta E, it's probably I have to calculate of 0.4 less accurate than the other transformation. But of course, I will say 0.4, nobody sees that delta E. So for me, it's better to go with this one where only the 2 channels are defined. And I can also say a big advantage is to keep the separation, the black separation. Because if you're doing an ICC transformation, it's always can happen that you are doing a re-separation of the data. With a DeviceLink, you can say, okay, I would like to keep the separation of my original source profile, so that the black is the same, or it's nearly the same, as near as possible. One thing, I'm just taking my mobile to see the time. Okay, good. Another possibility is that many printers are asking, well, I've got so many data, but I do not like to change my data because the customer sends me the data and I would like to keep it. But one thing is that it's important to reduce the total amount of ink on the paper. So do you have here something? Yes, it's possible with a DeviceLink profile that all other colors are not changed except in the shadows. So you can create a DeviceLink profile, which is also the TAC profile. TAC means total area coverage. Those DeviceLink profiles are within the pdfToolbox, and they will just reduce the TAC, the total amount of color, but all other colors won't be changed. So that means that 50, 50, 50, 0 will be the same on the output. But 350%, 330% of total amount can be reduced up to 300%. So it's written also in the DeviceLink. ISO quoted version 2, TAC 300 or TAC 270. So that means that just in the shadows, the total amount of ink will be reduced. But of course, if I'm reducing from 330% to 300, that means that the 300% has to be moved a little bit to make area for the 330% color. Here, for example, I converted with such a profile. We have here 280%. So here this color has 308% total amount of color. And after DeviceLink conversion with a TAC DeviceLink, everything will be reduced. And so the greenish area is not there anymore. So it's a big advantage for the printers. The powder is less on the output paper. They can go faster in the binding and cutting and stuff like that in the post-production. A third advantage of a DeviceLink is the so-called safe ink. So that means you can reduce the amount of ink on the paper because, as you know, a brown color tone, brown, can be defined with cyan, magenta, yellow, a certain brown tone, or I can say, no, I would like to take a lot of black and just a little bit color to color the brown tone. So with two CMYK definitions, I have the same brown tone. And safe ink means to reduce the amount of colors of CMY and increase the black. It's a kind of GCR. You could also say an ICC profile or a DeviceLink profile with the highest GCR is also a safe ink profile. It's a kind of little bit of marketing also. What's safe ink and what's GCR? Because, yeah. So reducing the amount of ink, of colors, cyan, magenta, yellow, results in reducing the cost, of course, because you don't need to buy and print so many cyan, magenta, yellow. More stable print, shorter make ready time, better dry, and so faster finishing. Now, of course, often customers say, okay, now I have a safe ink profile and I save a lot of ink. But that means also that the quality goes down. That's not true. I created, for example, a safe ink profile and I calculated, as you will see now, the delta E. What means that? Saving, for example, 20% of ink on the plates. How many delta E? So I have here the total area coverage, or 33% means on the plate, on this plate, 33% is dots of, or 33% is English, it's difficult. It's covered, right? It's covered on the plate, and magenta 36. And if I'm doing safe ink or high GCR, I increase the black, of course, but the colors are lowered, and so I save 20% of ink coverage. So I made this transformation through the safe ink DeviceLink. And then I calculated what means that for me. Here you will see also the plates, so the CMY and the black on the left side, and on the other side you will see the black plate is stronger. And this is the important slide. After safe ink I have an average delta E of 0.7. And of course, because I lowered also the TAC, the dark tones, I have a maximum delta E of 2.5. So that
between original and result.
Yes, right. So what I have done, I've done nothing. CMYK converted to LB the image. Then the CMYK image, I went through the DeviceLink, CMYK, safe ink, CMYK. And this CMYK again to LAB, I had two LAB images and I compared them. And so I got the delta E here. Okay, so thank you for your attention so far. If you have now any question, please feel free to ask. Yes?
On the question regarding delta E, what values are considered as large values and what are considered as small values?
So the one rule which is very easy to remember is a delta E of 1 and below, of course, is so a delta E of 1 and lower can't be differentiated by a human eye, of course normal observer, on a perfect condition. So that means everything is gray, you have a perfect D50 lighting, so you can't distinguish a color difference of delta E of 1 and below. 1, delta E of 2, 3, so there starts very slowly that you can see differences. It's also important to understand that in the grays we are more accurate, or we can distinguish much faster a difference than in highly saturated yellowish tones, for example. And that's the reason also, just some information, there are different delta E formulas. So that's delta E 76, that's the oldest formula, the easiest one, and delta E 2000, delta E 94, and so on. And the newer formula, they are considering also that in the grays, we are seeing much faster difference than in the highly saturated colors. Yeah.